quick pre-video, we're going to take a look at a review of what we've learned so far with OLS and generalize it. And then we're going to give you their first taste of some model selection. So here we are, ordinary least squares. We've seen it all. I want to give you the big recap. So we start off with the notion that we're trying to fit a model where we're predicting an output y value given some inputs x and a set of weights w. Now critically, what's going on with these variables here? Well, the x variable, the inputs, it can be multivariate. So when we are looking at the entire training set, which is what's going on with this capital X notation, right? The capital X means a matrix, and that matrix represents the entire data set. Well, that matrix X has rows that represent data points. So if we have n data points, actually n plus 1 because of the way I've zero indexed this, but if we have a bunch of data points, each row is a data point. This is our design matrix. And each column is a variable. So, these variables, we don't know what our problem is. If we're just regressing on just one thing, then we'd only have one variable. But if we're regressing on multiple possible inputs, we have, in this case, up to d variables, d dimensions, and data points. Okay, so critically, for our formulation to hold, we need to have a zeroth column. See, we've got zeroth variable here, right? And that zeroth variable is always going to be ones, because that ones column gives us the bias term. When we have wx plus b, we would, want to regress on both the x term, which is what's going to happen with these variables out here, regressing on the x's, but we also need a y-intercept, a bias, a constant. And that's going to be here in this zeroth column. Okay, so if x is d variables wide, well, w, our parameter vector, has to be a column vector that same size going up to d. And we can have this matrix be however many data points there are in our training set. So n data points, d variables. Okay, so our notion of regression is that we want to minimize the error, the difference between the true y values of each one of these data points, right? So y is going to be a vector that is a column vector that's the same height as the number of data points. Those y's are the true values. In the meantime, running our x variables through this parameter, multiplying the two together, gives us a predicted y value, a y hat. Y hat is what our regression is estimating. Okay? So the difference between y, the truth, and y hat, our estimate, that's an error, and we call those residuals in regression. So ordinary least squares is the loss function when we take our loss as being the error squared, the error vector times the error vector. And when we do matrix multiplication with E transpose E as the loss, what we get is the residual sum of squares, RSS. So these residuals, E, each single one of those variables, if it's n long vector, each one of those entries gets squared, and then each one of those squared entries gets summed together. That's what this matrix algebra does. Okay, How do we find the best possible W? Well, because this is a squared, right? This is a quadratic in y. Sorry, it's a quadratic in W, because y hat has got a W in it. So this is going to be quadratic in the weights. This loss surface is going to look like all quadratics look. In multiple dimensions, it's some kind of conic section or parabolic section. I shouldn't say cone, it should say can't say that. Parabolic section in however many dimensions there are in the weights or in the variables. And so how do we do that? Well, we want to find the W that's right here, down at the very, very bottom. And because it's parabolic, we know that it has one and only one solution, because it's a convex function. So that means that what we can do is we can take E transpose E, we can plug XW in for Y hat there, and we get Y minus XW transpose Y minus XW. That's just directly following from that. So we're going to minimize this function. We're going to minimize it. We're going to find a W star such that the gradient of the loss function is set to 0. Well, first we better get that gradient, right? So if we take this, right here, this plain old factored thing, just like we've always done in all algebra, we can just do first, outer, inner, and last. We can get all those terms. We can do some linear algebra that we went through last class, and we can knock it down to, and then once we've done all that, we've got the 4 terms, and then we take the partial of those 4 terms with respect to W, because that's what a gradient is. It's the partial with respect to W. Well, those 4 terms knock down into 2 because because of algebra and the fact that one of those terms is a constant with respect to W. That's how we get down to here. We went through it last time. I'm not going to go through it this time. Well, again, we find W star when we set this equation equal to 0 and solve for W. So a little bit more algebra, we get down to this. Now, this can be implemented easily. So here's a bit of NumPy code. We just have to set up XTX and do the inverse of that. So here's X transpose matrix multiplication with X. Take the matrix inverse, multiply with X transpose again, and then just take all of that and multiply it by the Y. So this is a little bit of NumPy code that will take a matrix that looks like this and give you an answer on what the optimal weights will be. Okay, so that's it, ordinary least squares. This is our formulation. Now, what if we want to apply that to a problem? Well, what should our model look like? What are those W's? We've got different choices of how to set up that model W. Okay, so what could different models be if we're trying to regress this thing? In this case, maybe we've got a bunch of data on moms and babies. And here we have, for instance, one measurement that could be an X variable, which is a hormone level in mom. And on the Y variable, maybe what we're trying to do is we're trying to predict the birth weight of the baby. Okay, well, we could fit a line, linear regression, right? That's a model. It's a kind of model. But it's not their only choice of model. Maybe we don't want to fit a linear regression. Maybe we think that this is more accurately represented by some sort of polynomial. Okay, that's a different form of model. So when faced with these 2 models, how do we choose the best possible one? Well, one thing that we really need is we need a metric to compare the models. Which one is best? So if we have two models, we need two of the same kind of measurement for those models, and we can compare those metrics and pick the one that has the best metric. Now, for machine learning in general, half of the thing is, hey, what is our comparison point, right? It's important how we pick this metric. So an obvious thing that you can always do with any machine learning function is start with the loss function. So if the loss function is a good representation of solving the problem well, which you kind of hope it is, then you can start with the loss function itself. So in this case, residual sum of squares, right? Because these are regressions, and their regressions fit with OLS. This is a small pause where I wait for you to think about, wait, ordinary least squares, I thought it was a linear function. And one of these is nonlinear. So how can you use a linear method on a nonlinear model? Well, see, I'm glad you asked that, because it turns out that the linearity that we're talking about is linearity with respect to the weights W. It is not linearity with respect to the x's. And we can use exactly the same math, just like we've been talking about, to fit either a univariate model with just one x, or like we've been talking about, a slightly more general case where you have multiple x's and you're fitting y in a multidimensional space. Or you can fit in this multidimensional space, instead of being x1 and x2, two separate x variables, well, you can have x1 be the x variable itself. And you can have x2 be not a brand new variable that's not estriol, but some other measurement. You could have it be estriol squared. So if this next column is, we have just one x variable, but we have the x variable here, and we have the x variable squared here, and we have the x variable cubed here, and we have the x variable to the fourth power here, then what we're fitting is up to a fourth power polynomial. Okay? So we're going to talk more about that later. But let's just imagine, knowing that I'm claiming right now that the math is absolutely identical, that we get some measurements, right? So between these three different methods of fitting, one, we're fitting estriol levels raw with a linear model. Here we're fitting estriol levels and we're putting in a fourth order polynomial. And here we're fitting estriol levels of mom and some other hormone. I don't know, we'll just make one up. And we're still trying to predict birth weight. So of these things, one of them has the lowest number and therefore assumedly is the best model. But I'm going to leave you with this. Which data set should we be comparing on? We have training data. Would it be best to do the training data? Should we do testing data? Data that is held out to guess about how good we're going to be in the future? Or should it be validation set? What is validation set? What is the difference between training, validation, and testing? Well, I'm glad you asked. We'll talk more about that during lecture. Bye for now.